Every square is a tiny spin. Some point up, some point down. And because they point in random directions, they cancel out. No direction, no order, no magnet. So how does randomness become magnetism? To understand that, we use one of the simplest models in physics, the Ising model. Every spin has only two choices, up or down. And every spin only talks to its nearest neighbors. The rule is simple. Neighboring spins prefer to align. Same direction means lower energy. Opposite direction means higher energy. That is almost the whole model. But there is one thing fighting against that agreement. Temperature. At high temperature, the system is noisy. Spins keep flipping. Small ordered patches appear, but they disappear again. Nothing survives long enough to become a magnet. The average still cancels out. But now we cool it down. The random flipping becomes weaker. The alignment rule starts to win. At first, only small regions agree. Then these regions grow into domains. Inside one domain, many spins point the same way. But different domains can still disagree. So the system is not one magnet yet. It is many tiny magnets fighting for space. Then the domain walls move. Small islands shrink. Large domains grow. One direction spreads. And slowly, local agreement becomes global order. No spin knows what the whole system is doing. Each spin only follows its neighbors, but together they organize. Now most spins point the same way. They no longer cancel out. They add up. A macroscopic direction appears. That is magnetization. A magnet is not ordered because every spin is controlled from above. It becomes ordered because many local interactions reinforce each other. At high temperature, randomness wins. At low temperature, alignment wins. But the most interesting place is the boundary between the two. Near the critical temperature, the system looks different. It is not fully random, but it is not fully ordered either. Clusters appear on many scales. Small clusters, medium clusters, large clusters. The system is balanced between disorder and order. That is what makes a phase transition special. And there is one last strange thing. The rule never preferred up or down. Both directions were equally allowed. The physics was symmetric. But once the system orders, it chooses one, up or down. The law is symmetric, the final state is not. That is spontaneous symmetry breaking. And that is why this simple grid is so powerful. Two spin states, local interactions, temperature fighting order, and from that you get a real physical idea. A magnet can emerge from macroscopic rules. A magnet is what happens when many small parts stop cancelling each other out and start behaving like one thing. Order does not always need a plan. Sometimes it only needs the right rule.